Okay, so this is Unit 6 and special trig integrals. So we have already seen that u substitution can be used to find the antiderivatives for tangent of theta or for cotangent of theta as shown. And we already know that the antiderivative of sine of theta is negative cosine and that the antiderivative of cosine is sine. But to find the antiderivatives of secant and cosecant, normal u substitution will fail. So we need to manipulate the integrand in order to make this work. So if we have the antiderivative of secant x dx, our first step is going to be to multiply the antiderivative by secant x plus tangent x over secant x plus tangent x. And this is just a fancy form of 1. So distributing, we then have the antiderivative of secant squared x plus secant x tangent x over secant x plus tangent x dx. Now, if we let u be secant x plus tangent x, our du is going to be secant x times tangent x plus secant squared x dx, which we can see with just some reordering of the terms gives us our numerator. So that means we now have the antiderivative of 1 over u du, which we know is the natural log of u plus c. So substituting in, we have the natural log of secant x plus tangent x plus c. I'd like you to go ahead and do example 2 and find the antiderivative of cosecant x. Now, on some occasions, it's going to be advantageous to use a trig substitution to find an antiderivative. Several of the commonly used trig identities are shown below, and this is, of course, not an exhaustive list. So, to start with, on example 3, we have 1 plus tangent squared, which we should recognize as the antiderivative from 0 to pi over 4, the square root of secant squared theta d theta, which is the antiderivative from 0 to pi over 4 of simply secant theta d theta. Well, we found this in the example above, so we have natural log of secant theta plus tangent theta evaluated from 0 to pi over 4, and I'll have you go ahead and evaluate that as part of your questions after this. Okay, so for this next example, we're going to end up using what we are going to call the power reduction formulas. So we know from our pre-calculus days that the cosine of 2 theta can be rewritten as 1 minus 2 sine squared theta. So if we start with cosine 2 theta is equal to 1 minus 2 sine squared theta, we can solve for sine squared theta as 1 minus cosine 2 theta over 2. So now we can rewrite this integral as the antiderivative from 0 to pi of 1 minus cosine 2 theta over 2 d theta. Now this is going to be advantageous to write this as 2 separate integrals. So we have 0 to pi of 1/2 d theta minus the integral from 0 to pi. I'm going to go ahead and factor out that 1/2 of cosine 2 theta d theta. We're going to leave that first integral alone for a little bit, and we're going to set u to be 2 theta. du is 2 d theta. du over 2 is going to be d theta. Because we have a definite integral, I know that u of 0 is 0, and u of pi is going to be 2 pi. So now we have the antiderivative from 0 to pi of 1/2 d theta minus 1/4 the integral from 0 to 2 pi of cosine u du. So this gives us 1/2 theta evaluated from 0 to pi minus the antiderivative of cosine is going to be sine, so minus 1/4 sine of u evaluated from 0 to 2 pi. Now the sine of 0 is going to be 0 and the sine of 2 pi is going to be 0, so we end up losing that term completely and we end up with just simply pi over 2. Now for this next example, we're going to define this as, I'm going to call this the odd man out. And to solve this, we're going to choose the sine or cosine term that has an odd power. We're going to convert part of those to the other term using our Pythagorean identities. So in this case, we have sine squared x. I'm going to write cosine cubed x as cosine x times cosine x dx. Cosine x, I'm going to convert to sine squared x, as this will be 1 minus sine squared x times cosine x dx. Distribute, we have sine squared x minus sine to the 4th x times cosine x dx. And now we can use u substitution. So u will be sine x, du is cosine x dx. And so now we have the antiderivative of u squared minus u to the 4th du. We know that's 1/3 u cubed minus 1/5 u to the 5th plus c. And substitute our u's back in. We have 1/3 sine cubed x minus 1/5 sine to the 5th x plus c. This is the rule that we call odd man out. So every time you're going to choose the odd power, convert all but one of those terms to the other trig function, and then integrate using u substitution. Okay, so the next rule that we're going to do, and these are in the practice page after the notes, is called the Stephen-Todd rule. And as you might imagine, they're going to apply with secant and tangent. So if an integral contains positive powers of secant and tangent, and the power of secant is even, you're going to save a secant squared for a du and convert the rest to tangent. If the power of tangent is odd, then you're going to save a secant theta and a tangent theta for du and convert the remaining tangents to secants. So let's look at this first one, and I'm going to just pretend that this is not a definite integral just to work our way through this. So we can rewrite this as secant to the 4th theta, tangent to the 4th theta, d theta. So we have even powers of secant, so we're going to save a secant squared for d theta, for du. So this becomes secant squared theta times secant squared theta times tangent to the 4th theta d theta. We're going to convert this secant squared to tangent, and so we have secant squared theta times tangent squared theta plus 1 times tangent to the 4th theta d theta. And so we end up with, we have tangent to the 6th theta plus tangent to the 4th theta times secant squared theta d theta, and then it's fairly easy to see that u will be tangent theta, du is going to be secant squared theta d theta, and we have then the antiderivative of u to the 6th plus u to the 4th du, which gives us 1/7 u to the 7th plus 1/5 u to the 5th plus c, or 1/7 of tangent to the 7th theta plus 1/5 tangent to the 5th theta plus c. So in problem 4, we have that the power of tangent is odd. So we're going to rewrite this one as secant squared theta, secant theta, tangent theta, du, or d theta. And we're going to set our u to secant theta. Du is secant theta, tangent theta, d theta, and you can see that we then have the antiderivative of u squared du, which is 1/3 u cubed plus c, and so this antiderivative is 1/3 secant cubed theta plus c. I'm going to skip to the end, and I'm going to do one other example where we can look at this from both sides. So if we have, for example, the antiderivative of secant to the 4th x tangent x dx, we can do this using both of the methods. I'd like you, so if we convert this using the Stephen rule, we're going to have secant squared theta times secant squared theta times tangent theta. Oops, these are all supposed to be x's, so let's fix that. And then convert, so secant squared x, this becomes 1 plus tangent squared x times tangent x dx, or tangent cubed x plus tangent x times secant squared x dx. And I'd like you to go ahead and finish integrating that one. If we do this using the Todd rule, we'll have secant cubed x times secant x tangent x, and I'd like you to go ahead and integrate that one using and see what the difference is between your two final solutions.